Hello and welcome to the course Basics of Experiment Design for Cognitive Psychology. I am Dr. Arik Verma from the Department of Cognitive Science at IIT Kanpur. As you know, this is the third week and we are talking about experimental designs. In this lecture, what I will do is I will take you through the mechanics of experimental design. Remember, in the previous class we adopted a modeling approach, which was basically proposed by Cunningham and Walraven in their book. We are sort of going with that model and we are trying to understand some of the fundamental principles in experimental design. Okay. So, let us revisit that. The idea was that a model of human behavior, or say for example, whatever cognitive function you want to study, let us say you want to study word recognition, or let us say you want to study, say for example, contrast perception or size perception or orientation perception, anything for that matter, which are typical subjects of experimental psychological studies. We basically have the model m of x is equals to b of x plus EW. Now, just to revisit this, m of x is the measurement in a measurement term in a given experiment. It has all the information that there is one trial, single participant, what are the conditions, what kind of situations are there, and everything condensed together in this one variable. This is the measure that you are getting in one trial. What is b of x? B of x is whatever mental functions, perception plus action, whatever mental functions were sort of involved in producing this measurement. So, basically what is this measurement measuring? This measurement term is measuring the mental functions that are going on inside the person's brain to lead to the given response, all right. So, b of x. So, that is basically and we will use this term again and again. This is referred to as the perception action loop, all right. Now, you will see that there is also this error term in there. What is this error term? Error term basically, or error W, EW, this one here, this error term is basically the error in this that error that is combined with this perception action loop, which the measurement also gets. The idea is that this measurement does not always get the exact representation of the perception action loop. There is always some error. What is the source of this error? This could be just random background neurons firing, some kind of environmental variables, some kind of subject related variables that are creating slight variation. Remember, we are talking about the pointing example, that if I want to point at a specific place in my hand and I am making this action again and again, it is not guaranteed that I will reach or touch the exact same point on the hand at every trial. If I want to ensure that, then I will probably need to be very slow and very conscious in making that action movement. So, the thing is, every time you do a behavior, every time, say for example, you are, let us say you are doing a word recognition experiment. Typical word recognition experiment is like there is a blank screen, there is a fixation cross, there is a word, you have to tell whether this is a meaningful word or not. Now, every time you are making that same decision about different kinds of words, so there are word level characteristics and there are participant level characteristics that will lead the reaction time to be slightly different every time. Okay. Even if it is the same word that is presented, let us say on trial number 10 and 15 and 20 and 25, you will see that the reaction time might be slightly different. It is not going to be identical, let us say 552 milliseconds. It will be probably 552 milliseconds on one trial, on another trial it might be 500 milliseconds, or another trial it might be 600 milliseconds, all right. So, that is basically what this error term is. Now, what are we conducting this experiment for? Just let us revisit that. We are conducting this experiment to get a good estimate of the mental processes or the cognitive functions that are involved in a particular decision. So, whatever task we are doing. So, let us say we are doing a reaction time experiment to a lexical decision reaction time experiment. So, m of x is basically the reaction time, the measure which is seemingly capturing what is happening inside behind this response. So, the process of lexical access plus let us say some error, all right. So, let us go forward and see how this pans out. One of the things that we basically do in experimental design is basically we need to take a number of measures. It is not, for the most part there are no single trial studies. There are single trial studies where you have too many participants, you can have a single trial study. Typically you have few participants and a lot of trials. Why do we need so many trials? Why do we need, say for example, for a single measure, let us say even if I have a single word to which I want to know your response, whether it is a word or a non-word, why do I need, let us say 5 measurements for it, or 1 measurement, or 50 measurements for it? Let us try and understand that. So, the method for isolating B of x, as we have just said, derives from the observation that while this error term EW is different every time we measure it, our underlying perception action loop, this B of x, is constant. So, the brain is actually following the same process to arrive at the decision whether a particular stimulus is a word or non-word. The error term might vary, and that is what is basically creating the disparity between your responses. So, 552, 602, 752 or even 452 milliseconds, that error term is changing across every trial, and that is what is causing the change in your reaction time. All right. So, this is the fundamental assumption in this research, although if you remember in one of the courses I have talked about the central identity theory, the type and the token identity theories and so on, where people have argued that is it exactly the same set of mental processes, does the brain follow the exact same algorithm every time it makes a similar decision. Again, that is a debate for another day, but let us say that is the assumption with which we are conducting these reaction time studies. Also, one of the things is that behavior does change over time. So, for example, on the first trial versus on the 50th trial versus on the 100th trial or the 500th trial, in the same lexical decision task, I am getting some practice with this. I am getting basically some kind of learning that okay, how do I decide whether this is a word or a non-word? Maybe I am making a strategy, maybe I am sort of just referring to the sound whether it is familiar or not, whether I am basically just going to, oh, I know this word or not. As a participant, I can be using any number of strategies, all right, but my strategies will get better over time, and that is why in large scale lexical decision studies you see that there are block effects. Typically participants will start somewhere around 600, 700 milliseconds. By the time they sort of are at the 10th block, 50th block, 100th block, it sort of reduces by around 10 to 15, 20%. Okay, so there is effect of learning, there is effect of practice that is there on behavior, and that is all right. I think the mental representations get sharpened, the response perception action loop gets sharpened, all of that happens. Okay. But the evidence of from current research basically suggests that B of x, this perception action loop, broadly remains constant. So, the source of this variation or whatever learning we are getting, it does not drastically change or reorganize the perception action loop. So, mx is equals to bx plus EW, this bx for the most part remains pretty much constant. That is basically why we conduct these experiments, hoping that in every reaction time we are actually indexing that same mental process, lexical access, let us say. All right. So, evidence suggests that B of x will stay mostly constant over short periods of time, which is why it is suggested to carry out the experiments with a limited period of. So, again the practice effects that I was talking about, while there is, yes, there is evidence of the fact that B of x remains typically constant for periods of time, but if this practice effect, if the session is too long, if it's something that you're doing for several hours at once and you're doing it for every day, let's say you're learning to play guitar and you're learning to you're having your guitar classes 1 hour for every day for a continuous 30 days or 60 days or 90 days. Now, your performance and the mental circuitry that is leading to that performance from the first day to the 90th day might change a little bit. In that sense, that is basically why it is suggested that when you are doing these experiments, do not have too long experiments. There are effects of fatigue etc. that come in, but practice effects over long periods of time are certainly to be avoided, and that is why within 1 to 2 hours this B of x is least changed, and that seems to be the best time to conduct this experiment within. All right. So, this is something that we have this idea of. Now, error in pointing, let us say you remember the pointing experiment we are talking about. So, the pointing experiment is that there is this bullseye and we have asked our participant to come and touch at the center of the bullseye. The participant has come and touch at the center of the bullseye. On trial 1 he was off by 1 millimeter, in trial 2 he was closer, in trial 3 suddenly he was off by 5 millimeters. So, we are conducting this over a number of trials. The idea is that this measure how far off the our participant is from the bullseye, that that is the dependent variable that we are saying, and that is basically coming out indexing your mental process plus this error term. So, this error can be different. It can be different on every trial. Say for example, in sometimes it will be to the left of the intended midpoint, sometimes it will be the right to the intended midpoint. There is no, if there is no constant pattern in this error that constantly it is offset by 10 millimeters to the left, there is nothing to worry about. It will probably average out over a number of trials. So, averaging over several measurements will typically give us a decent estimate of what B of x is all about. Okay. That is, by the way, why we were conducting this experiment in the first place. Okay. So, just look at this set of equations here. If we repeat this experiment exactly, conditions etc. being identical over a short period of time, then the average pointing accuracy will give us a good estimate of the underlying pointing ability, the underlying mental abilities, cognitive functions that lead to this particular pointing ability. All right. So, the same, if you want to state it in form of an equation, this is basically what these guys have done. So, m1x is equals to bx plus ew1. So, this is the first error term, second error term, you summate it over a number of trials, you get a decent estimate of m of x becomes almost equivalent to the b of x, because this error term sort of cancels out over time. The more measurements you take, the smaller the error term will tend to become. It is getting averaged over time, sometimes to the left, sometime in plus, sometime in minus, and so on. Now, when we have multiple measurements of multiple trials of this particular term, so m of I given a situation x, and this x remains constant across different measurements, understand this one very important thing, that these measurements will all not be identical. Okay. And while we previously stated, we have defined the output of B to a constant, let us say there is a constant situation, the trial is similar, the all the other conditions are similar. So, any differences that happen across measurements are basically due to variations in this error term, again something that I was already saying. Now, as mentioned, it is very unlikely that this error term will become 0 at any point in time. It will not become 0, it will reduce to a certain negligible thing. Okay. So, with two measurements, let us say you have two trials, trial number 1 and trial number 20. With two measurements, it is more likely that the average will be close to 0, but this is again still very improbable, it will reduce. If B of x is actually constant and the situation x is absolutely identical, then this variance will be small, and then the two measurements might be enough to isolate the actual mental process that we are after. So, that is basically the idea in these repeated measurements. Okay. However, you have to understand that it will be extremely difficult to ensure that x is absolutely identical across trials. What is this x? Remember, single trial, whatever the conditions are, whatever the participant's mental state is, whatever the stimulus etc., mental stimulus and other environmental things are. So, obviously there will be some random variations at both ends. So, it will be difficult to make it absolutely identical. Firstly, and there are several reasons of it, there are two of which we can point out. For example, the mere passage of time between the two trials may mean that the physiological state of the participant will be different. Okay. When he came, he was thinking about something else. After one or two trials, he is now thinking about something else. When he came, he was not ready to do the trial. Now he is already motivated. Something has happened. Across trials, also the participant is getting probably more engaged in the task. So, they are slightly more alert, slightly more anticipating, and that reaction time is reducing. Or maybe the task is boring. Towards the end, again the participant is getting fatigued or bored, and the reaction times are again increasing. So, across measurements, it is important to understand that these things will not be identical. Passage of time, conditions change, that happens. Second is, first trial can essentially be seen as an opportunity to practice this task. So, you are going to get slightly better, there will be practice effects, there will be order effects. Okay. So, typically what is done is, if I remember correctly, a lot of times when experiments have a large number of trials, it is always a good idea to basically look how the participants' responses have changed over time across trials. So, something that you used to do a lot is basically you can calculate the split half reliability. Let us say there are 100 trials, first 50, last 50, basically calculate the correlations so that the responses are not too different from each other, and therefore, that is how you can take the overall average and work with that. All right. Now, all in all, what really is going to happen is that more measurements will mean a greater likelihood that the error term will be small, negligible, and in some sense factor itself out of the equation. Your measure becomes closest to this perception action loop that you are trying to anyways estimate. All right, and this is basically very common in classical psychophysics experiments, where tens of thousands of measurements are taken for each condition and each participant. All right, but in typical experimental psychological studies, if you see that number of trials is not too many, it's around 20, 40, sometimes 60 trials per condition, and that's broadly assumed enough. So I did a lot of laterality experiments during my PhD, and the largest number of trials per condition I had, and there were 8 conditions, so it is a longish experiment, was around 60 trials per condition. Probably in one experiment I had 80, but 40 to 60, 80 is broadly enough. And there is something that also is important, is the effect size. When the effect sizes are large, say for example, when you are looking for left hemispheric lateralization of word processing, then the effect size is typically larger, and then you will need fewer trials to get closest to that B of x that you are after. But in cases, say for example, when you are looking for symmetry judgment, or you are looking for some kind of right hemisphere task where you are looking for overall contour judgment, things like that, where the effect sizes are relatively smaller compared to left hemispheric lateralization for words, then you will probably need a slightly larger number of trials. There are obviously statistical calculations that allow us, that help us to do this, but we will talk about them as we go forward. Now, we talked about multiple measurements. Why did we take multiple measurements? But we also use multiple participants in our experiments. Why do we need multiple participants? Let us talk about this. So, given that if we have multiple measurements, we can sort of make reliably definitive claims about the specific situation x that we are measuring, and a natural part of the measured situation is your participant. So, are there errors? Is there error because of the participant level characteristics? If you have 1, 2, 3, 4, 5 participants, each of these 5 participants are not going to be exactly identical to each other. Okay. On papers may be the same age, same gender, same educational qualification, same SES, yes, but as individuals they are different people, and because they are different people, the effect that they will have on the error term is going to be different in your experiments. All right. So, if you measure only one person, we can talk about only that person's results and that person's perception action loop, that B of x that we are talking about, but we do measure many people, and how is that justified? So, we have no idea, within this, you remember the specificity versus generality example, we have no information about how other people would perform. Maybe they will perform in the same manner, maybe they will perform very differently, maybe they will have other strategies and other personal level factors that will play a part. So, how do we get around this in our experiments? So, measuring more than one person will typically yield more than one measurement. So, you will have, let us say, m of x1 and m of x2, something like that. So, it should be possible to basically use these multiple measurements, like rather than repeated measurements of an identical situation, to isolate B of x. What are we after? This mental state B of x, and we want multiple measurements across number of people, not multiple measurements within. So, we are not talking about repeated measures at this point, we are talking about multiple measurements across different people. Now, if this B of x, this mental thing, this let us say lexical access for word recognition, is identical for all people, then measuring one person many times or many people one time is basically the same method, because the mental function is pretty much the same, and it is, in that sense, you can use either of the two. Unfortunately, we know that in almost no real world case is B of x perfectly identical across people. People have different experiences, different strategies in which they will do the task, different skill sets, phenomenal things, and so on. So, B of x is never perfectly identical across people. Okay. So, what we do is, we can assume that B of x contains some element that is constant across all people and some element that varies across people. Okay. So, in other words, what we can do is that we can assume that there is a constant population level perception action loop and there is a individual level perception action loop. So, generally one person's way of accessing the semantic network to perform lexical access is this individual strategy, and it is obviously, if you have read research by Quinlan and Dyson and some of these Collins and Quillen and those kinds of papers, you know that semantic networks are basically affected by personal experiences. So, one person's route of reaching a given word may not be obviously identical to other person's route of giving reaching a word, but across the population there can be a population level perception action loop, population level mental function that is basically leading to this successful lexical access. And then obviously there are individual level processes for lexical access. This would be similar to the assumption made for M of x, where each person has an underlying perception action loop and each measurement is a slight deviation from it. So, M of x is equals to B of x plus there is a person level error term, because that is the one that will be different across each individual. Okay. So, how do we model it? We can model it in two ways. We can basically look at two kinds of error terms here. The first error term is this original error term EW. This is called the within participant error term. So, within participant, if you compare measurements trial 1, trial 2, trial 3, trial 4 and so on, there will be some variation in this error term, and that is called EW or within participant error term. Now, obviously we have multiple participants for our experiments, that can be introduced by this error term EB, which is this between participant error term. Between participant error is broadly difference in characteristics which are leading to difference in this error term across different individuals, that is broadly. So, now your M of x is equals to just look at this, M of x is equals to B of x plus these two error terms. Okay. So, we are basically making this assumption rather explicit that there are these two error terms that are independent of each other and can be linearly combined. You are basically not saying that they are interacting or something, we are saying one is within participant error, one is between participant error, and you can basically combine them to get a overall idea of how much error there is going to be in your measurement M of x. Okay. So, this new error term will affect the number of measurements that we will need, just as this within participant error term did. Also, the larger this between participant noise or error will be, the more samples we will need to be sure to have the best approximation of B of x. Okay. So, that is broadly how we talk about this. So, we have M of x is equals to B of x plus EW plus EB, and you will need several measurements to reduce this EB to a smaller, more negligible thing. And if you have enough measurements across enough number of participants, the assumption will be that this M of x will be very close to B of x, and the EW and the EB, error within participants and error across participants, will both be sort of neutralized, minimized and sort of rendered out of the equation. All right. Now, how do we know how many participants or what can be used to decide this? There are obviously power calculations and other statistical methods, but what is the concept behind this? Okay. One of the things that people have used a lot is historically they look at the literature, they look at the number of similar studies, and they use that to guide oneself to the ideal number of participants. More recently, however, people do best power calculations, and power calculations give you on the basis of effect sizes and confidence intervals the exact number of participants you need for a given experiment. Okay. Let us try and understand that conceptually a little bit, although. So, in many low level perceptual processes, basically say for example, you want to detect the processing of line orientation, detection of motion, detection of contrast, those kind of things, the between participant error variance is found to be very small, it is typically very small. So, as long as we are sure that we have a good estimate on the for each specific person, between within subject error is less, basically by running several trials for one given person, then even a small sample size of 4 to 5 people would be sufficient to yield a reliable estimate of this entire population level perception action loop or this population level B of x. On the other hand, when you are talking about higher level processes that are sort of affected by individual experiences, let us say such as the ability to solve math problems, this E of B can actually be quite large. Okay, and because it is quite large, you will need more power, you will need many more participants to get closer to this B of x that you want. So, as more variance is expected, many more participants shall be required. As effect sizes are smaller, many more participants are going to be required. Now, this is one of the reasons why for which many cognitive psychology experiments have hundreds of participants. Sometimes say literality experiments you see that have many participants. Okay, typically, and especially if you are doing right hemisphere functions, there are large number of participants that you need. Not a few participants will not do, because the effect sizes you are typically hunting for are very small. And previous studies will tell you, look for this effect size, these confidence intervals, and nowadays we use G power. It tells you that a large number of sample sizes is needed. Also, the number of conditions that you need. If you have 4 conditions, you will need adequate number of measurements for each condition. That sort of multiplies and basically increases the amount of participants you need. So, if we further assume that within this, coming back to this, if we further assume that the within participant variance EW is similar for all people, we can use a large number of people just with one trial per person in order to estimate the underlying perception action loop for all people. So, that is also one of these ways that you can follow. See, again remember, the trade off is between number of participants or number of measurements per participant. That is broadly a rule of thumb that one can follow. Now, also it is important to note that in some cases the variance between participants EB can be extremely large, which would tend to make it harder for experimenters to precisely measure the effect in which they are interested. So, that basically confounds this a little bit. Alright. For instance, it might be the case that the population has a bimodal distribution, that is, there are 2 distinct subpopulations, one of which is very accurate and the other is not. It will be helpful then to have an idea of the source of variation. Okay. So, what can happen is that you have one set of population extremely proficient, extremely good at the task, and they get this done very quickly. Okay. So, if we further assume that the within participant error term is similar for all people, then basically what we can do is we can use a large number of people with just one measurement each, and that works. But in some cases this this EB, this error between participants, is quite large, and given that it is quite large, what will happen is that it will become harder for experiments to precisely measure the effect in which they are interested. Okay. Sometimes you can have very different populations, say you are doing a language proficiency task, or you are doing a lexical decision task, or you are doing a language switching task. You will get extremely proficient participants who are very good in the given language, let us say English or Hindi, and you will get some participants who are not as good at, say for example, you are doing an English word recognition task, who are not as good at that. So, you will get almost 2 different distributions. What the idea here is that if you get to the source of the variation, you can try to control for it. Suppose in language switching experiments, people get to see that okay, the exposure is the issue, the exposure to the second language is the issue. Once they figure it out, they control and match for the amount of exposure of the language that is there, and that basically allows them to control for this between participants error and keep the sample sizes to tractable distance. Alright. Now, the final thing that we can talk about here is, so we have talked about repeated measures, we have talked about across participants. We should also talk a little bit about different conditions. I was just telling you about literality experiments. There are sometimes around 4 to 8 conditions in these experiments, and across condition also there will be some error. So, let us see how this it works out. In order to average the number of measurements, this M of I that we were talking about, to approximate this perception action loop, every aspect of the situation, this x must be identical across samples. Okay. Any difference from one trial to another will add to the noise. So, this random variation from Bx, this some error term will get added. For instance, changing the participant from one measurement to the next also alters the situation. Adding this variance caused by this change of participant as an explicit term EB shall also allow us to isolate this B of x very quickly. Now, if we go with this assumption that all other possible changes are also independent of each other and can be weighted linearly and added together, then what we can do is we can also have an error term with respect to the different conditions that are there in the experiment. Remember, I was saying if we have more conditions, even more measurements are required. All right. So, if we go with the assumption that all other possible changes across conditions, across participants and so on, all other changes are also independent of each other and can be combined weighted linearly, then basically what we can do is we can add this other error term across with these measurements and basically work with that. So, we can basically add more measurements for this condition term as well. So, the idea is that your equation will now become m of x is equals to b of x. You have error between participants, error within participants and error for each condition. So, the number of conditions you have, you will also be adding to the error, but again what you can do is you can keep on adding the measurements to reduce this error term as well, which will get you eventually closer to the b of x that you are after. Okay. So, with reference to the pointing example, remember we had this bullseye where the participant is coming and touching the center of this of the target. So, with reference to this pointing example, we can say that let us say contrast is different from one trial to the other. In one trial there is a 100% contrast, and the other trial there is a 50% contrast. Now, this change of contrast in trial number 1 and trial number 2 will cause some change, some additional error will be caused, and let us say that error is basically represented in this E of C, this the third error term that we have in this equation. Now, if we know that a small contrast change does not really affect performance and it does not cause any additional error, the changes are all small, then this contrast will not really need to show up as an error term here, because we know that it is equivalent to 0 and it will go away. But sometimes what will happen is that we will need to explicitly control for it, because we know that it is going to cause a difference in the reaction times or difference in the overall performance. So, we will need at least two measurements, let us say one with a high contrast target m of x and one with a lower contrast target m of x plus let us say this delta c. There is and this delta is basically the difference between contrast on first target and contrast on second target. In this case, what we end up doing is we are explicitly varying our stimuli along a given dimension, and basically what we are doing is we are getting the effect on b of x of this variance in dimension. Let us say we are talking about word recognition, I was talking about lexical decision task. Now, in this lexical decision task, my words are varying on this dimension of frequency. Some words have a frequency of 10,000 per million, some words have a frequency of 1 lakh per million, and some words have a frequency of let us say 100 per million. So, I have 3 levels. Now, the thing is, in the 3 trials where these 3 things are coming, I will need to what I am doing is I am basically creating frequency as a factor, very low frequency and high frequency. This different levels of a given dimension are called levels. Factor is frequency. What is the factor? Factor is frequency. Factor has 3 levels: very low frequency and high frequency. In the contrast example, what we have the factor is contrast. There are 2 levels: low contrast, high contrast. So, we have now basically error coming out of these two. This difference in contrast between the two is probably also creating some difference in the reaction time pattern, some difference in the mental process that are going on, which we are also interested in finding out and measuring. And basically this is the one what is referred to as the variation of or variance in independent variable. Okay. So, because it is the the only thing that determines the levels of a given factor is the experimenter, and because they are independent of this actual experiment, that is why they are referred to as the independent variable. Remember, we have several other variations of this also. Why is an independent variable called an independent variable? Because it is independent of the experiment, but in control of the experimenter, who sort of can vary it independently of everything else. Okay. Remember, the underlying assumption in experimental psychology is that the independent variables are also independent of each other and can be weighed as a weighted linear sum. We will talk about this when we talk about interactions and stuff. Now, complete combination of factors and levels for any single trial can be referred to as a condition. So, what is a condition? Condition is a high frequency condition, low frequency condition. So, we can have different things. If there are 2 factors with 2 levels each, typically what we will have is 2 cross 2, we have 4 conditions. Okay. Let us say I was looking at I want to look at the lateralization of tools. Now, I have 2 kinds of stimuli, tools, non-tools. How will I test lateralization? I will use lateralized presentation to the left visual field and to the right visual field. So, one factor is stimulus, it has 2 levels, tools, non-tools. Another factor is visual field, it has two levels, left visual field, right visual field. 2 cross 2, we have now 4 conditions. Each of these conditions will have their own error term, and we will need an adequate number of measurements in each of these conditions to basically get closer to the B of x that we want. Alright. So, some changes across conditions will be trivial and will not affect our measurement, and to determine the question of which changes will be important and which are not, that is basically what we try and handle in experiment design. Okay. Now, our a priori hunches about what changes will affect our experiment will not always be accurate, and hence without knowing beforehand which factor will play a role and which will not, the best strategy is to make all trials as identical as possible along all dimensions, even things like apparatus, room in which the experiment is being conducted, noise levels, etc. So, you do not measure different conditions in different conditions here, these these 4 conditions, you do not measure them differently, you measure them within the same experiment with all things being equal. Only the thing that is different is, say for example, tool versus non-tool, tool in left hemisphere, tool in left visual field, right visual field, non-tool in left visual field, right visual field. So, what we try and do is the only difference will be the one that you are actually wearing, all the other things are to be kept equal. Okay. So, let us look at this in terms of this pointing experiment. So, going back to this pointing experiment that we started with, pointing to a high or a low contrast target, we have one factor with 2 levels. What is the factor? The factor is contrast. What are the levels? High and low. Note that the 2 conditions are broadly identical, with the sole exception of the fact that just the contrast is different. This difference can be represented by saying that one of these conditions is a baseline and the other is the experimental condition. So, let us say we say 100% contrast is baseline condition and 50% contrast is the experimental condition. We are studying the effect of lowering contrast levels, that can be done. Okay. So, equation wise, just to sort of make sense of this in the model that we are talking about, mx is equals to bx plus error within participant, error between participant. Now, we what we do is both sides we have a delta c, the error because of condition, and this side also we have error because of condition. Now, what we have this whole equation, if you take the difference between first and 3, what you basically get is you can get closer to the effect of condition, effect of contrast change in this specific example, which is your B of delta c. What is basically happening in the brain, in the mind, whatever you want to use, with respect to this conditional change, and this is what we are after in experiments. So, error between participant, yes, error within participant, yes, but what are you after when you are having these multiple conditions? You are looking at the effect of the condition on the mental process. That is what B of delta c is. Alright. So, you basically, that is basically what we are after. Now, how much of this effect, say for example, when you go from 50% contrast to 100% contrast, how much change happens? Let us say the reaction time changes by 50 milliseconds or 100 milliseconds. Remember Sternberg's example of search thing, every single term that you are adding in memory, it was basically leading to 40 millisecond increase in the reaction time. Alright. So, this this difference in conditions that is happening in the brain or the mind is basically referred to as effect. That is the very broad, slightly loose definition. When there is a large effect, it would basically refer to a large difference in performance between the 2 conditions. Say for example, difference between word and a non-word. So, status, if wordness is the factor, then word and non-word reaction times are very different. The reaction times are faster for words. How much faster is your effect size? Okay. However, if B delta c is large, then it will be easier to detect. If it is small, it will be difficult to detect and you will need more measurements. That is what we were talking about. So, a large value of this B delta c can be detected even with an imprecise estimate of the error terms EW and EB, and small effect sizes will basically get masked by large error terms. So, basically when you are looking for small effect sizes, you want the error terms to be even more negligible and minimal, and that is what will make you have more and more measurements. Okay. So, conceptually, obviously, a lot of us as you know, a lot of people as students will just enter you know, what is the effect size you are looking for, confidence etc. in the G power thing and get their values out, but this is the conceptual you know, underlying principle, that why do you need the error terms to be small, why do you need you know, the effect size to be large. That is basically what we are trying to talk about. So, this is broad idea of how and what are the fundamental principles in experimental design within a modeling perspective. We will talk about you know, we will extend this example to other domains in the next lecture. Thank you.